Thank you all for joining the webinar. We will begin shortly. Thank you all for joining this afternoon's webinar. I hope you can hear me well. My name is Dan Munteanu. I'm a technical consultant with manufacturing group with SolidCAD. On another line with me is my colleague Robert Piccinich, industry account manager at SolidCAD, and he's going to watch the chat window. Please post your questions in the chat window, and we will answer them after the webinar by email or by phone. In this afternoon, we're going to take a quick look at Autodesk Netfabb solution, and we hope you'll find this of much interest and use to you. So Autodesk Netfabb is, as you probably know already, is a solution for additive manufacturing and end-to-end solution. Let's start by presenting the agenda here. So a few words about SolidCAD, Netfabb, its role in your process, and an overview of the Netfabb modules and functionality. SolidCAD, founded in 1996, is currently Autodesk Platinum partner and the only Canadian Platinum partner with Autodesk Advanced Manufacturing Specialization. Since 2017, SolidCAD is a member of Cancel Group as it's currently the largest has the largest team of specialists in Canada. And industries that we support are AC, BIM, civil infrastructure, manufacturing, plant and process, media and entertainment. And as activity fields, we are involved with training, consulting, data management and collaboration, workflow optimization, simulation analysis and technical support, and software development. Autodesk has, SolidCAD has a number of training facilities across Canada and is authorized training center from coast to coast. As a member of the Cancel Group, that can offer a full set of services in the engineering, surveying, construction, mining, from surveying geomatics, wide format and supplies, mapping and GIS, construction supplies, and printing. At SolidCAD, we support a number of other solutions to help our customers Let's take a look at the Autodesk Netfabb toolset. As I mentioned, Netfabb is showing a complete workflow for 3D printing, supporting a variety of processes and machines. Here is a list of 3D printing processes: material extrusion, fused filament fabrication, and also known as fused deposition modeling, resin or VAT photopolymerization, both stereolithography and direct light processing, powder bed fusion as polymer and also as metal. On the metal side, direct metal laser sintering, selective laser melting, electron beam melting, binder jetting, and also directed energy deposition. Over 200 machines are currently supported from almost 30 manufacturers. The important part here to note is the fact that Netfabb can communicate directly with these machines and send the build files to ensure quality build. Currently, the Netfabb solution is comprised of Standard, Premium, and Ultimate products, one building on top of the other's functionality. On top of that, we have a set of utilities that will help with the process. For example, optimization utility, advanced toolpath utility, lattice topology, as well as a Netfabb simulation utility. And we'll talk about this a little bit later. So let's take a look at each of these products. Netfabb Standard covers all the important aspects of creating a model from bringing the geometry in as mesh, 3D CAD or slice files, having the ability to export the mesh back to CAD as BREP, boundary representation type solid, model editing, for example, part hollowing, tools for mesh manipulation, applying labels, textures, colors, having the ability to cut, split, or shell the model. Slice commanders with toolpath simulation and being able to create hatching patterns and offsets. Let's take a look at some videos here, courtesy of Kevin Morsfield, technical sales specialist from Autodesk. And first we'll look at mesh to BREP export. So this is the interface of Netfabb. We're bringing in a mesh solid as a 3MF file on a generic platform. We have the ability to orient the model here, and we're going to apply some mesh modifications. For example, we're going to extrude some of these bosses. We're going to look at the repair part first, see if there's any need to fix the model, and we will extrude the selected surfaces at, say, a value of 5 millimeters. The preview is going to show us how the result is going to be. And in the next step, let's delete some of these faces. We're in a repair environment now. Different options there. Also the ability to cap the mesh model. And the modification could be kept as a separate part, or applied, I mean, remove the original part, or keeping the original as well. And next step is going to be to export this to Solid. That needs to happen after a check on the surface health, looking for normal reversals, or any kind of missing missing geometry. So we need to make sure that this is a watertight solid. The export could happen maintaining the sharp corners of the part, or applying rounds, especially for components that are a result of generative design process. And this is the final result. So a model that has been exported, that could be exported to STEP, SAT, or IGS. Some other functionality in Netfabb Standard, ability to fix meshes, look for missing triangles, overlapped geometry, by applying some scripts for automatic meshing, semi-automatic process, or a fully manual process by replacing triangles. Netfabb Standard also allows a basic 3D packing, like a 3D nesting algorithm, which will take care of collision avoidance, planar packing, ability to move, rotate, or align the parts, orientation analysis. In terms of machine workspaces, it does not support metal type machines, so it's FFF and not metal. Also, the ability to create fused filament type supports at the toolpath level, so inside the G code. The next level, Netfabb Premium, expands on the capabilities of Netfabb Standard, and allows for advanced 3D packing, automatic sorting by size using a couple of highly optimized 3D packing algorithms, Monte Carlo and Scanline. Also, it supports automatic generation of complex lattice structures, and to that extent has a couple of utilities very useful, as well as the ability to create a variety of supports. Let's take a look at another example here. So you see here in this example on a generic platform, a set of parts of various sizes. We're going to bring in another one, small component, and we want to make sure that all these copies, let's say 25 of them, are not going to be lost in the packing algorithm, thrown in the volume. So we're going to make sure they're kept together. So we're building a package around them, and that allows us to keep these components organized together under that pack. The 3D packing, Monte Carlo algorithm will, as you'll see in a bit, will take care of organization of these to optimize the space. Next step, we're going to take this and place them in a specific machine bed. So I'm going to use a let's say a HP Jet Fusion 3D printer, and we're going to add these components now to the build zone. And again, make sure that these components are kept together by grouping them. And as you will see, after we start the packing process, these components are going to stay under the defined package. There's no interference between components. There's no collision. They are arranged to optimize the volume. Okay. Here's an example here of a lattice commander. So with lattice commander, we're again bringing a mesh file in from a large number of formats, and the intention here is to lighten up the part. So we're going to remove some of the geometry, some of the faces, and replace those with an automatically generated lattice. So we've dragged the component into the lattice commander here, and we're going to shell this and then remove some of the faces. Here's a volume lattice command, so we're going to apply a X type topology for this, and these parameters are used to define the lattice size, the three directions, as well as the thickness of the elements. So this lattice is basically matching currently the volume of the part that we started with, and it's a separate component. And the next step is going to be to vary some of these thicknesses. So we have the ability of controlling areas where the lattices have a different thickness than the general one. So start thickness and an end thickness, in this case, equal. You can see in between the two defined planes, the model has now a thicker thickness than the 1 millimeter we started with. Now, the next step, we're going to apply an operation that will allow us to basically merge all these together. So removing some of the faces first, thickening some of the remaining faces. The intention here is to apply modifications to the solid that will ensure a certain mass reduction and strength as well. So the result now, it's going to be basically a Boolean operation between multiple components that will allow us to obtain the final part. And here it is. Some slice planes will show us the geometry change in and different lattice thicknesses, different wall thicknesses as well. Lastly, Netfabb Ultimate, again building on top of Netfabb Premium functionality. There are some extra features there in Lattice Assistant, editable cell size, variable scale for cell size scaling, lattice optimization to withstand prescribed static loads, as well as the selective space structures, 3S. This will allow us to customize lattice patterns and unit cell topologies. Okay, here's the Lattice Assistant here. Okay, we're again adding a component. This time is a native SolidWorks file, and the intention here is to reduce the material that we're going to use to build the part by hollowing the interior, replacing the solid interior with a lattice structure. Okay, so this component is a solid component at this point. And the type of lattice structures available, you can select them from a long list. Also, the thickness can be defined here and the cell size. And again, in 3 different directions. And let's see what the result is going to look like after post-processing. We're going to apply some holes to be able to remove the powder. Software also has the ability to create plugs as separate components in case you want to actually plug back the solid and glue it back together. You can see the holes being automatically applied there. And cross-section through the model shows the lattice structure that was generated. Okay. Also part of Netfabb Ultimate, there's an advanced toolpathing utility which allows the tool to connect directly with the machines and create machine-specific build files to ensure that quality of the print is the best possible, and the print is happening at the highest speed. So that's all based on machine properties in let's say a post-processor specific to the machine. Some other capabilities also, scripting with Lua scripting language to automate common preparation tasks, as well as Netfabb application server. So this will allow us to install Netfabb on multiple computers on a network headless, so without an interface, again, to speed up the processes. Lastly, let's talk a little bit about Netfabb Simulation. So these builds, especially on the metal side, are particularly expensive. So the intention here is to make sure that we avoid build failures. And in order to do this, we are going to use this weakly coupled thermo-mechanical model that will allow us to predict residual stresses and excessive distortions. On the example on the left side, you see there the part distorted again upwards and separated itself from the support structure. So you see all that break zone example. On the right side, again, the part distorted upwards and passed through the powder bed level. The recoater blade hit at that point the part and broke it. So these are the kind of things that we mainly want to avoid. Netfabb simulation as a workflow, it's basically combining a thermal and a mechanical analysis. So we have as inputs material properties and machine process parameters. The heat transfer analysis gives us a temperature history, and that allows us to find the deformation in the structural analysis and get the final product, the output being the deformation, the displacement. As typically simulations are iterative processes, there is currently a manual optimization iteration that needs to happen. So what we're doing here is we're capturing the material properties, the process properties into a so-called PRM file, a process parameter model file. And this is using something called multi-scale modeling. So basically a really small model on the left side, which its properties in terms of a moving heat source can be now applied to a 3D CAD model that you see on the right side. So going from a small size to a part scale geometric model. So this PRM file will allow us to store these material properties like thermal conductivity, specific heat capacity, elastic modulus, yield stress, coefficient of thermal expansion, all these being temperature dependent measures, as well as density, as well as process parameters. So laser power, scan speed, spot size, layer thickness, hatch spacing, and rotation. They all part of this process parameter file. By having this process parameter file, we can now extrapolate this to various CAD models, and you can see results of some simulation on this type of parts. Here's a screenshot of the out-of-the-box Netfabb PRM files. Various alloys, Inconel, titanium alloy, and so on. And here are some examples of the simulations based on the problems described. So you can see the area here where the recoater blade would hit the component, as well as the area on the right side where the stresses are too high and the support separates from the model. A few other applications of the Netfabb simulation utility: ability to determine hotspots and areas that suffer from a lack of fusion, consequently weaker, being able to simulate an annealing process, stress relief treatment, being able to predict the residual stresses after wire EDM removal of the component from the build plate, and being able to use distortion prediction to create and export a compensated shape. So if this is the geometry we need to end up with, the simulation will allow us to see where the stresses are going to be built up, and the material will be basically pushed out, which allows us to define a compensated geometry that we're going to actually build, and as a result of the heat transfer process, we can end up at that point with a proper, correct nominal geometry. In terms of packaging, Netfabb Simulation is it's coming in basically two products: Simulation LT, which is included in Netfabb Ultimate, and there are some limitations here. 500,000 nodes, the size of the model, 20 layers grouped maximum, and there's a process of in order to reduce the amount of memory and the processing time required, there's a process of coarsening the mesh, for example, in the build area, and there's a maximum of 2 mesh coarsening generations there. Also, there's no moving source. This is a part level powder bed fusion only. As a separate product, installing Netfabb local simulation, these limitations are removed, and this allows us to also simulate a directed energy deposition process and create custom PRM files. Thank you. I hope this has been useful as a quick introduction. For questions, these are the email addresses. And thank you all for attention.